All right, we're back again. Oh, that's my YouTube screen. Here's what we want. Nope, not those. That's where I kind of got all this stuff. Here we go. All right, so let's move this ladybug back over here. And I went to the ladybug, sorry. All right, now, some things with Snell's law, all right? And apparent depth, all this. Now, notice, this sunken chest is way down here. But when you shine a light or when you're looking at it, if it's in really clear water, because it's going from air to water, it bends this way. And you go, oh, it looks like its apparent depth. The apparent depth makes it look like it is up here. All right. This is why I got soaking wet. Now, this is a good, remember this formula, okay? I'm gonna write the apparent depth because I like a problem. I like problems that deal with apparent depth, okay? So this is where it appears. This is where the object appears, and D is equal to N2 over N1, all right? Where N2 is where the observer is, okay, and N1 is where the object is. See, because here's N1 down here in the thing, and so it's actual depth, and D is the actual depth. All right. So let's just take the apparent depth D prime. Watch me do this. Okay. So here we go. So we've got, where the hell is it? So we've got D prime is equal to D times N2 divided by N1. All right. So this is why, like, if you're on the diving board, if you're on the diving board, the diving board, and it looks like the apparent, and it's supposed to be 10 feet, okay? You're on the diving board, you're looking at the 10 foot, and you're looking at the drain through the thing. It looks like it's supposed to be 10 feet underwater. Well, D is equal to 10 feet, but you are looking at it from N2 is equal to 1.00 from observer on the diving board. So if you're up here on this diving board, looking down into the water at the drain down here, which is 10 feet down here, okay, and you're looking at this drain, you think it's 10 feet, but it actually looks to you like it's up here because N1 is equal to 1.33. Now, so therefore, the apparent depth, D prime, is equal to D times N2 over N1. Okay, so you just wrote the same thing twice. Because, why? Because you're a Nimrod. And then, so this is equal to 10 times 1.00 divided by 1.33, which is like 1 divided by 4/3, which is like 3/4. So this comes out to be 7.5 feet. Okay, so actually, that's the apparent depth. Now, the flip side is if you're in the water. So now let's say apparent depth when you're in the water. The apparent depth when you're actually in the water and you're looking at the diving board, the 3-foot diving board, it looks pretty far away. If you're down here with your little goggles on, you're looking up, okay, with your little goggles on. I don't know why I drew my head so funny, but anyway, you're looking up here with your goggles on, drew a little pig in the water, all right? And this is 3 feet, but now you're in N1, which is equal to 1.33, and the diving board, the 3-foot, the small board is N2, which is at 1.00. Okay, so you're in the water. Boy, I hope I'm doing this right. I'm doing it completely wrong. This is N2, and this is N1. There we go. Knew I was up to something. So therefore, the apparent height, or the apparent depth of this thing, is equal to the real is 3 times 1.00, 1.33 divided by 1. So that comes out to be what? 9.99 times 3. I can't. 3.99. 4. It's approximately 4. So it looks further away. Looks further away. All right. Let's keep going. Oh, yeah. Directly to the swimmer, the coin appears to be at a certain height above the water. Is the apparent height of the coin less than or greater than? It's greater than. It's greater than. All right, this is how the displacement cells. So this is, they're getting into the theory behind it. Now, here's the critical angle. This is really cool stuff. This is really cool stuff. So we've got this this total internal reflection, and it comes when we have the critical angle. And you can only have total internal reflection when you're going from a medium of higher index of refraction to a medium to lower index of refraction. Because look, if N2 is greater than N1, I get a number bigger than 1. That doesn't compute. So I guarantee you, because you'll have a question like this on the exam, I guarantee you 3 or 4 of you are going to jump into it, get it backwards, and go, my calculator is saying it's an error. Well, yeah, because you're trying to find the angle, the critical angle of something that doesn't exist. You can't. You're trying to divide by 0, basically. You can't do that. All right. Because look what happens. So you got an incident ray. It's coming in. It's kind of small. It's really a tight angle. It's really a tight angle coming in. Boom. It's got a reflected ray. And then when it comes in here, notice that the refracted ray goes right along the surface of the water. And then if I come in at an angle even bigger, it's totally internally reflected. Okay. So the sign of the critical angle there is N2 over N1. And so this is why diamonds look very sparkly in air, because they've got, notice, a beam of light is propagating through a diamond, strikes the diamond air surface at an angle of 28 degrees. Will part of the beam enter the air, or will there be total internal reflection? Repeat part A, assuming that the diamond is surrounded by water. Okay, so if it's coming in at 28 degrees, because actually the critical angle for a diamond, I think, is 24 with air. Okay, I mean, we could compute it really quick. And so if it comes in at 28, it's going to just bang around inside there. The critical angle of a diamond is 24.4 degrees. So if it comes in at 28, it's going to be totally internally reflected. When it's in water, when it's in water, some of it is going to get out because it's, even though it's in the water, the critical angle of the critical angle is changed because of the two mediums. And so the 28 degrees is not changed. Since the 28 degrees is less than 33, some of it's going to be reflected back in, but some of it is going to get out. Whereas at 28 degrees, when it's coming in at 28 degrees, it's going to get bounced out. It's going to stay inside of me completely. I'm getting tired. I should probably stop. But we're doing good, though. What's next? Because of light coming, it glitters. Because all the light that's hitting it, a lot of the light that's hitting it is interfacing with at less than the critical angle, so therefore it's staying inside and giving its luster. If you place it in water, more will get out, and so it kind of loses a little of its brilliance when it's in water. Okay, and they use this total internal reflection for cladding and stuff like that. Polarization, Brewster's law. Meh. So since we talked about polarization and we're looking at angles of reflection and refraction, yeah, go with this. Yeah, this is a good thing to do. Okay, Bruce, I don't think I gave you any problems on it though. So, but Brewster's law is a tangent B. I think we should probably practice a problem or two. So, and we should probably stop this silliness.